So welcome back to another day. Today's big topic is we're going to return and finally get to answer that question we asked a long time ago. How do we figure out area? So we've got a diagram here. So the green line represents a nice graph and the black lines represent an axis. And our goal is to figure out how in the world do we compute this area in here. Okay, so it's not a nice triangle or square, rectangle, something with a nice formula. So what we do first is we say, well, instead of getting the exact area, let's just go for an approximation, because something's better than nothing. And so what we do is we break the area up into 4 different regions here, and we use these 4 rectangles to approximate the area. And what we can see is we did a pretty good job. We got a good area here. The problem, of course, is that this area up here, that's all going to be a little bit of error. And so what we want to do is we want to minimize that error. And one way to make smaller error is to use more rectangles. And so it's kind of easy to see that visually what we've done is we've taken and we've removed these error terms. If you figure these out very carefully, you would have less error than you did before. The problem is that to calculate these, this is going to be a lot of tedious busy work, right? You'd have to find the height of this rectangle, the width, the height, and the width, all kinds of measurements in order to obtain an area. And if you decided you wanted more accurate information, well, you'd have to redo it all again. It'd just be a lot more work every single time. So instead what we want to do is we want to figure out a better way to do this, a way to do this without having to use so much work and having to repeat our work every single time. We kind of want to do our work once and then use it to get an accurate answer. So one of the tools we're going to need to use is a new notation style in order to keep track of this idea of adding up all of our rectangles, or adding up lots of things. So let's review some notation styles first of all. So first of all, if you ever had to add up 3 numbers, one of the first things you learned is, well, right here, what I've got is I've got 3 2's, so I can write this as 3 times 2. Also what I could do is if I had to add up 4 2's, what I could do is I could notice, well, there's 4 of them, so I can write this as 4 times 2, and these will get the same answers, and so this is a good notation style. Well, another thing you could learn to do is you could say, well, suppose I had to add up some unknown quantity of 2's, let's just say there's n of them. Well, how could I write this? I could write this as n times 2. I've got n 2's, so I take n times 2 to get my answer. And this is a really nice shortcut formula for adding up the same number over and over again. The issue now is we don't want to just add up the same number. What we want to do is we want to figure out ways to add up certain patterns of numbers. And for this we need something that's going to be called sigma notation. So here's our new notation called sigma notation. It's named after the fact that this letter here is a nice Greek letter called a sigma. You've probably seen it on some fraternity and sorority shirts on campus. And what it stands for is it stands for sum. Sigma and sum sound similar, so we use the letter sigma. And it's going to be our notation for adding up lots of stuff. So lots of vocab words here. The letter I is going to be called the index of the summation, so that's our index. AI is going to be the ith term of the sum, so these are going to be numbers or symbols, and they're going to appear over here. And then we also have the upper and lower bounds of the summation. In this case, our upper bound here is going to be n. It tells us when to stop. And our lower bound in this case is 1. It tells us where to start. So I know this looks a bit confusing, but let's look at some examples, and I think it'll make more sense. So here's our first example. We say that this is the sum from I equals 1 to 5 of I. So written out. So here we have it written out as a sentence, and the key features is that all these are pronounced the same. It's going to be the sum from the lower bound, including the index, to the upper bound of your pattern. And so what this pattern really means is it means what we're going to have is we're going to have, starting counting at 1, we're going to have 5 terms in total. And so the 1 comes down here and tells us to start at 1. And the 5 tells us that we're going to have 5 terms in total in all. And what the I tells us in here is this tells us the pattern to follow. So here are our i's. So our first I is 1, and our pattern tells us we're just going to use I, so just 1. Plus, next we're going to add to this using I equals 2, 2. Plus using I equals 3, 3. Plus using I equals 4, 4. Plus I equals 5, 5. So the key thing to notice is down here we have the i's, and up here we're going to add together the patterns. And then what we of course need to do is we just need to add these all together, and if we do all of our arithmetic correctly, I think we end up with 15. So let's see a few more of these just to get used to them. So in this case, we've got the sum now from I equals 0, so good thing to know is we start at 0, we end at 4, and we have a new pattern I plus 1. So let's see, we're going to start with our i's, so we're going to have a 0, a 1 term, 2, 3, and 4. And what we're going to do is we're going to use this in our pattern here. So if we put 0 into our pattern, this means our first term will be 0 plus 1. Plus we'll add to that now with a 1 plus 1. Plus 2 plus 1. I've gotten a little off here with organization. Plus 3 plus 1. Plus 4 plus 1. But in each case, I've used my I in my pattern here. And so what we can see is that if we simplify this a bit, well, we get 1 plus 2 plus 3 plus 4 plus 5, which again makes 15. So this sum gave us the exact same answer as our last sum, even though it looked quite different. It just depends where you start and where you end. Very different looking sums can give you the same answer. Very similar looking things can give you very different answers. But let's look at another example. So now let's look at the sum from I equals 1 to 5 of I squared. And of course you should always be pausing the videos to try to see if you can figure this one out before I write out the answer. So in this case again, we're going to start with a 1. So we're going to have in total 5 terms because we're going to go from 1 to 5. And our first term, we're going to put 1 into the pattern, so it's 1 squared. So we have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And you would add those all up on a standard calculator and you would get a number. And I believe that number is 55. And it is. But now we're going to do 2 more examples with slightly more complicated patterns to follow. So in this case, if we look at it, our patterns do 2 things to notice. First of all, we're starting now with a k instead of an I, but that's okay. We're just going to have k's are the variables in our formulas now. And we're going to stop at n. So we're not going to stop at a number. We're just going to have a bunch of different things to write out. So what this tells us is that, yeah, we can go ahead and we can say, well, we're going to start at 1, then we're going to have 2, 3, but we're just going to keep going until n. So what this means in our first pattern is that we're going to have still the 1 over n, because remember that these numbers are our k values, times 1 squared plus 1, plus 1 over n times 2 squared plus 1, plus 1 over n times 3 squared plus 1, plus dot dot dot, plus in the last one, 1 over n times n squared plus 1. So certainly we can't just go ahead and add these all together now because it's pretty abstract, but it still is a pattern that we can repeat and write out. And in just a little bit we'll learn how to deal with things that look like this. Finally, here's a really confusing looking example. It's got all kinds of weird symbols in it. So here we've got i's, we've got deltas, all kinds of stuff. But again, we simply need to follow what the pattern says. It says to start at 1, so our first entry will be f of x sub 1 times delta x, plus f of x sub 2 times delta x, plus dot 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 dot, plus f of x to the n, because we're stopping at n, times delta x. This is really abstract. There's nothing much you can do here. All we can really do is unpack what the symbols are really telling us. Now in these summations there are certain patterns that occur over and over and over again, so much so that we want to develop some shortcuts to deal with them. And so what I have listed in the table here are several shortcuts that we can learn to deal with. Now, if we want to look at the first two, because what the first two say are really interesting things. They say that if you have k, and it's going to be a real number, and you've got it inside your summation here, basically what you can do is you can factor it out. Now let's think about why this works. Suppose you're told that you want to add up from I equals 1 to 3 5 times I squared. Well, what we know is we can unpack this. We're going to have three terms. We're going to have a 5 times a 1 squared plus 5 times 2 squared plus 5 times 3 squared. Since there's a 5 in each of these terms, we can go ahead and factor it out. So we have 5 times 1 squared plus 2 squared plus 3 squared. But then once you get pretty good at sums, what you can see is well, we have a pattern in here. We have a 1 squared, a 2 squared, and a 3 squared. So this is going to be the sum from I equals 1 to 3, since there's 3 of them, of I squared. And the net result here is we had this constant on the inside. We were multiplying by all of our formulas. And so what we can do is we can move the constant outside of the sum. And this helps us with simplifications. In a very similar way, property 2 tells us that if you have two patterns that you're adding or subtracting inside a sum, you can break these apart into separate patterns. And you can also go the other direction with it too. If you have two patterns, you can combine them together or separate them. So it's important to think about this in both directions. So suppose we decide we're going to add from I equals 1 to 3 again, I squared plus I. Definitely two patterns. Well, what this means is the first one is 1 squared plus 1 plus 2 squared plus 2 plus 3 squared plus 3. And we can reorganize these into 1 squared plus 2 squared plus 3 squared plus 1 plus 2 plus 3. And now these become nice patterns that we can write as sums. So this first one is just the sum from I equals 1 to 3 of I squared. And the second one is the pattern from I equals 1 to 3 of just I. So what we've done is we've broken one pattern up into two separate sums. So there's a great story in math about a mathematician whose name was Gauss. He lived in the late 1700s, early 1800s in Germany. And when he was in kindergarten, his teacher didn't really feel like doing anything that day. So the teacher said, "Hey students, why don't you go ahead and add up the numbers from 1 to 100. And the story goes that all the other students, were sitting down and they get to work on it. You could actually pause the video now and think about how long it would take you to add up the numbers from 1 to 100. Well, the teacher looked over at Gauss and saw that he just scribbled a few things on his paper, turned it over, and just started goofing around. Now, the teacher was quite upset, but, was feeling pretty lazy, so didn't do anything right away. Instead, waited till the end of the day and got up and, got over by Gauss and got ready to yell at Gauss. And she looked at Gauss and said, "Gauss, what have you done?" And Gauss simply turned over the paper, and on the paper had written just a single number, 5050. And now the teacher was upset because this was the right answer and wanted to know how in the world did Gauss figure this out so quickly. And so what Gauss's method was for adding up these numbers really quickly, first of all, I don't think the story is true, but it's a great story, so it's okay, is he took the numbers and he said, well, let's line the numbers up. If I have the number 1, the number 2, the number 3, line these all the way up, all the way down to 50. And then let's go backwards. So I've got 51, 52, with 49 above it. Go all the way back down, and I'll have 48. Whoops, sorry, wrong number. And of course, if I count correctly, I meant 98, 99, 100. So I've got all the numbers there. And let's go ahead and add up each column. And after doing a few, hopefully you see that they all add up to 101. And well, how many 101s do I have? Well, since I had 50 numbers, I have 50 columns, so I can just take 50 times 101, and I'll get 5050. and 50. And he was right. This was a really quick, slick way to add up all these numbers. And actually what this tells us how to do is this explains to us formula number 4 here. So let's think about this. And let's make room so we can write some stuff down to think about this. So what this summation over here in number 4 is really saying, and I've written it again here, is it's really saying add up the numbers that start at 1 and go up to n. Well, what Gauss would do is Gauss would say, okay, let's line up the numbers. 1, 2, 3. Keep going until you've listed half of your numbers, n divided by 2. And now what we can do is we can go with the next number, which is just going to be n over 2 plus 1. And we can keep writing them until we end up with n. And of course, the previous number was n minus 1. So this is going to be all of your numbers in a list. You add them up again. And well, what do you end up with? You end up with n plus 1, n plus 1, all the way down. If you write this out, you end up with n plus 1. Well, you have n over 2 of them, so this means that this should really equal n over 2 times n plus 1, which is exactly formula 4 there. It's exactly our shortcut formula. So anytime you want to add up the numbers from 1 to whatever number, you don't need to actually write out this pattern here instead. What you can do is instead you can just now substitute and compute using this formula. So for example, suppose we wanted to add up the numbers from 1 to say 1,000. Okay? Now this would certainly take you a long time to do by hand, but instead what we can do is now we can just substitute them into this formula. Run that through your calculator and you're going to get the answer. You're going to get the sum of the numbers from 1 to 1,000. So now let's look at how we can use these properties in a simple, more complicated scenarios that we're more likely to encounter. So let's look at this sum here and try to figure it out. Now, we don't want to write up all the terms. What we want to do is we want to write it as neatly as possible using these facts given up here. So the first thing we can do is we can rewrite this as a sum that breaks up it into 2 fractions. Now the reason I wanted to do this is because I saw an n here and I saw another n over there, and because n over n is pretty nice. N over n is just going to be 1. So what we can now do is rewrite this very nicely as the sum from I equals 1 to n of 3i squared over n plus 1. And now here's where we're going to start using our patterns. What we want to do is we want to think, well, which pattern does this one most closely resemble? And hopefully what you looked at is you saw, well, there's this plus in here. I'm adding up 2 different patterns. So I'm looking at this pattern up here, which says break it up into 2 different sums, because once I break this up, I'm going to have much easier things to deal with. Our goal is always to make the insides easier, because the easier they get, then we might have a shortcut formula for them. So now I can break it up into 2 separate sums here. So the first one is still pretty complicated looking, but the second one has gotten pretty nice looking. This second pattern here, if we look at it, we're just adding up a constant over and over again n times. So this is going to be this pattern up here, which is just adding up a constant n times. And so we'll be able to eventually replace this one. So for now we'll leave a space for our first sum, but this one is just going to be adding up 1 n times, so this will be our constant 1 times n. In our first pattern here rather, what we want to notice is we want to notice the I squared is kind of locked in there, but 3 is just a constant, and this n is just a constant that we can factor out. So in this case what we can do is we can use property 1 here to factor out our constant. So we can rewrite this as 3 over n times the sum from 1 to n of I squared. Now this makes me very happy because this pattern right here, the sum from I equals 1 to I squared, is exactly one of the patterns we have up here. We have a nice little shortcut formula for it. I'm not going to go over into how someone came up with that shortcut formula. Trust me, it was a lot of sleepless nights that accomplished that. But what it allows us to do is to use their work to make our lives easier, because now what we can do is we can rewrite our sum now as 3 over n times the pattern they found plus just n. And so this gets to be our final answer. No i's, no sums in it whatsoever. Now it's just ready for us to put in specific n numbers so that we can actually compute things. Now you're probably saying to yourself, in a very polite terms, Professor Williams, that was pretty confusing stuff. What in the world do I need that for? And I'm going to tell you right now what we're going to need that for, okay? It's not a big deal. So here's the basic idea. What we want to do is we want to figure out area. So what I want to do is I want to use 4 rectangles to approximate the area between the graph of f of x equals negative x squared plus 16 and the y-axis and the x-axis over the interval 0 to 4. And here I've drawn in the diagram of basically what I want to do. What I really want to do is my goal is to figure out this area in here between the axes and the green line. And to make an attempt at this, I'm going to start by saying, well, I can get myself an approximation of the area using these 4 big rectangles. And so what I can do is I can look at my first rectangle here, we're going to call R1, and we'll notice it has a certain height, which we'll call H1, and it has a certain width, which we'll call W1. And in fact, I have this for all of my rectangles. So I'll give each rectangle a name, and I'll give some variables for each of the things that I'm interested in for each rectangle. And what I really want is I know that the area of a rectangle R sub I is going to equal to, well, I just need to take the height times the width, and then once I figure these out, what I can do is I can add them all up. So in our new notation, what I really want is I want to figure out the sum from I equals 1 to 4 of HI times WI. And the reason I want to do this is because, according to my pattern, what this really is this is going to be H1 times W1, the area of the first rectangle, plus H2W2, the second area, plus H3W3, plus H4W4. That is, I'll have all of my areas added on up, and I'll get an approximation. And what I can actually see, too, is I can actually see, well, how am I going to do this? Well, there are lots of things I want to notice in my pattern here. The first thing to notice is that I chose my rectangles in such a way so that they each have the same width. That is, WI is equal to 1 for all of my rectangles. And then what I can do is I can look and see that what I've always done for each of my rectangles is I've used what's called the left end point. So what I did is I looked at the base of my rectangle here of W1, and then I had a choice, and I ended up using 0 for W1, and that's where I calculated my height, right here at 16. For the next rectangle, W2, I used 1, the left end point, to grab my height. Same for W3, I used the left end point, and for W4 I used the left end point again. So this is going to be my left end point summation. So in total, if I tried to calculate my summation, well, I would have to take 16, my height, times 1, plus next I would take my end point at 1, so at 1 I would get a height of 15 times 1, plus then at 2 I would get a height of 12 times 1, plus last I would get a height at 3 of, I believe, 7 times 1, and if I add these all together, what I end up with is 50. So my approximation for my area is 50, and as I can see, it appears to be a bit of an overestimate. So what I've done instead for this example is it's the same graph, it's the same function. We're still dealing with f of x is equal to negative x squared plus 16, but instead what I've chosen to do is I've chosen to do what are called right end points instead. So I still have a width for a rectangle, but now instead of going up at 0, what I've done is I've chosen to go up at 1 here to draw my rectangle in. Same thing with my second interval. At 2 I go up to the curve and draw my rectangle. With 3 go up to the left, or the right rather, And with 4, I actually have a height of 0, so I have a height 0 rectangle instead. And so today what we're going to do is we just want to keep practicing with these summations, getting used to this notation, and then tomorrow what we're going to do is we're going to see more about how to actually make use of this in order to create formulas that allow us to figure out these areas without doing too much work. It's really not too bad. We're not going to do too much measuring, we're just going to do a little bit of computing. But as always, try the problems posted online, post a question to Blackboard, and feel free to ask any questions you have. Thanks.